In mechanics of materials, there is one equation so important that without it, you cannot derive the famous bending equations. This equation is fundamental in the Euler-Bernoulli Beam Theory. It states that the strain is equal to the negative of the fiber distance over the radius of curvature. How was this derived? And what does it actually mean? Let's find out in this video. Here is the outline of the video. In the first part, I will briefly explain a few prerequisites for deriving the fundamental equation. This includes some observations from our experiment in the last video. Next, I will go over the notations, where I will assign the symbols. This will be followed by the results of the experiment, which is the derivation of the fundamental equation. Finally, we will discuss the interpretation of the fundamental equation itself. So, let us start. We already show from the last video that if we bend an object in this manner, the top portion got shorter, or in other words, it is compressed, and the bottom portion got longer. In other words, it is stretched. While the center, because the sponge has symmetrical cross-section, is neither compressed nor stretched. Now, for the notation. On the left side, you can see the sponge before it is bent. On the right is a drawing of that sponge. Now, we will take an element from that sponge. Because the sponge is symmetrical, the neutral axis is exactly at the center, just like what we showed in the experiment. Let's label the thickness of this element as delta x. Let's also label the distance of the fiber from the neutral axis as y, and the initial length of that fiber as delta s. Before bending, you can see that delta x is equal to delta s because nothing has happened yet, and the fibers above and below the neutral axis have the same length. Now, let's bend this sponge. We can observe that the center of the sponge did not change its length, but it became an arc, giving rise to a radius of curvature rho and an angle theta. Also, the distance y from the neutral axis is still the same because the vertical lines are just rotated. However, the length of that fiber in the distance y from the neutral axis has changed because it is compressed, which we will now call delta S prime. Now, we are ready to derive the fundamental equation. What we want is to find the normal strain due to bending. We know that normal strain is change in length over original length. We also know the fiber length before and after bending, the delta S and delta S prime. So, we just substitute this into the normal strain formula. The original length is delta S, and the change in length is delta S prime minus delta S. What we need now are delta S prime and delta S in terms of rho, the radius of curvature. We know that before bending an object, delta S is equal to delta X. Since delta X remains the same after bending, we can express delta S as the arc length rho times theta. Recall the arc length formula, that is S is equal to theta times R. Furthermore, Delta S prime can also be expressed as an arc length, but this time open quantity rho minus y closed quantity times theta. If we substitute this into the formula above, the thetas cancel out and so do the rho's in the numerator. This leaves us with a formula epsilon is equal to negative y over rho. This is the mathematical result of the experiment, which serves as the fundamental equation of beam equations. Now, let's interpret the equation one step at a time, and let us start with the sign. From the way we derive it, if epsilon is positive, it means that the fiber is stretched because y is below the neutral axis. Negative times negative is positive. Conversely, if epsilon is negative, it means the fiber is compressed because y is above the neutral axis. Furthermore, epsilon is proportional to y. This just means that the farther the fiber is from the neutral axis, the more stretched or compressed it is. More accurately, the value of strain varies linearly with the distance from the neutral axis. Lastly, the epsilon is inversely proportional to rho. This means the smaller the radius of curvature rho, the more compressed or stretched the fiber becomes. To visualize the interpretation, let me show you this. See side by side. Less bending results in a larger rho, while more bending results in a smaller rho. Because epsilon is inversely related to rho, the less you bend the sponge, the less strain the fibers feel. And the more you bend it, the more strained they become. Now that we understand the resulting equation from our experiment and the meaning behind it, we now understand the kinematic pillar of the Euler-Bernoulli Beam Theory. And we are halfway ready to derive the consequence of this equation: deflection, flexure, and transverse shear formula. So stick with this channel because we are going to derive them in future videos.